Hidden in Earth's atmosphere is a rare gas that once redefined how the entire world measured distance. This is Krypton, the element that changed science forever.
Right now, I want you to take a deep breath.
Yeah, seriously, just go ahead, a real deep one.
Inhale and just exhale.
There you go.
Now, as you took that breath, you probably didn't think twice about the chemical composition of what just filled your lungs.
I mean, most people just assume it's oxygen, right? Maybe nitrogen?
Right. It's mostly nitrogen, a good chunk of oxygen, maybe some argon and carbon dioxide in there.
Yeah.
But hidden within the very air you just inhaled is this impossibly rare, completely invisible element that most people literally never think about.
It is entirely silent.
Yeah.
Like, it's colorless, odorless, and completely tasteless.
It's just hiding in plain sight.
Exactly, hiding with every single breath we take, just constantly entering and exiting our bodies without leaving a trace.
We are talking about Krypton. And no, not the fictional home planet of a certain superhero,
Right.
but element 36 on the periodic table.
Right.
It's a noble gas, and its name literally translates from ancient Greek as the hidden one.
Which is just a perfect name for it.
It really is. Welcome to Atomic 118, where we are doing a deep dive into the story of the hidden noble gas. To understand how we found it and, what we actually do with it, we've brought a whole stack of sources to the table today.
We've got everything from these old historical logs written by late 19th century chemists to modern research papers on noble gas applications.
Yeah, optics, thermodynamics, all of it.
The overarching goal of our discussion today is to trace the journey of this gas. We really want to look at how humanity managed to isolate an invisible, inert substance that makes up just 1 part per million of the atmosphere.
Which is just a crazy small amount.
It is. And we'll look at how we subsequently harnessed its unique atomic properties to power cutting-edge technology, illuminate cities, and even redefine our physical measurement of reality itself.
Okay, let's unpack this, starting with the chemical identity of Krypton. So, sitting at atomic number 36, with the symbol Kr, it occupies that far-right column on the periodic table.
Noble gases.
Right, the noble gases. We're looking at a family that includes helium, neon, argon, xenon, and radon. And the defining characteristic of this group is their completely filled valence electron shell.
Yeah, they don't need to share or steal or swap electrons to achieve atomic stability.
They're just totally content on their own.
That atomic self-sufficiency is exactly what makes them so chemically aloof. I mean, standard chemistry is driven by atoms seeking a full outer shell, right? Which is what leads to bonding and folding compounds.
But Krypton's shell is already perfectly balanced.
Exactly. Because of that, it stubbornly refuses to engage. It doesn't burn, it won't oxidize or corrode metals, and it rarely forms chemical compounds, even if you put it under extreme laboratory conditions.
It exists entirely as a monatomic gas. There's these solitary atoms floating through the atmosphere. And we are talking about extreme rarity here.
Super rare.
Like nitrogen makes up about 78% of the air, oxygen is about 21%, and argon is just under 1%. But Krypton, it makes up only about 1 part per million.
To put that in perspective, you could fill an entire Olympic-sized swimming pool with normal air, and the total volume of krypton inside it wouldn't even fill a small water glass.
Wow, just a tiny water glass for a whole pool. And, it's crazy to think that Krypton wasn't even created on Earth.
Oh, yeah, it's basically ancient stardust.
Right. It formed billions of years ago inside massive stars. And when those stars exploded as supernovae, they scattered these Krypton atoms all across space.
Some of which eventually became part of Earth as it was forming.
So every single Krypton atom around us today is technically older than our planet itself.
Which means every breath you take contains tiny pieces of ancient stardust.
I just love that. But that extreme scarcity explains why humans breathed it in for hundreds of thousands of years without having the slightest inkling of its existence.
Yeah, discovering it required a fundamental shift in how we actually study the atmosphere. You couldn't just run air through a chemical filter.
Because Krypton won't react with the filter.
Exactly. So in 1898, scientists William Ramsay and Morris Travers had to rely on state changes. Specifically, they used the fractional distillation of liquid air.
And to do that, you have to subject atmospheric air to incredible extremes. They use this thing called the Joule-Thomson effect.
Right, which basically means compressing the air, removing the heat generated by that compression, and then allowing the air to rapidly expand.
And that rapid expansion causes a massive drop in temperature. If you cycle that process enough times, the air gets so unfathomably cold that it literally collapses out of its gaseous state and pools into a liquid.
It's wild to think about doing that in 1898, but once Ramsay and Travers had this beaker of liquid air, the separation process relied entirely on boiling points. Every element transitions from a liquid back to a gas at a very specific temperature.
So as they allowed this ultra-cold liquid air to slowly warm up, it began to fractionally distill.
The nitrogen boils off first at negative 196 degrees Celsius.
Okay, wow.
Then the oxygen vaporizes at negative 183 degrees, and argon follows shortly after that.
It's like a cosmic game of hide and seek. They were basically peeling away the loud, bulky layers of the atmosphere until only the stealthiest element remained.
That's a great way to put it, a chemical process of elimination. You let the abundant elements boil off into the room, and you carefully analyze whatever is left in the flask.
But hold on, the thermodynamics of this, they don't really add up for a standard 1898 laboratory. We just established that krypton is 1 part per million, right?
Right.
So to get enough liquid air to isolate even a tiny, measurable bubble of pure krypton, Ramsay and Travers would have needed industrial-scale compression. I mean, they couldn't have just chilled a small flask on a lab bench and magically found element 36.
What's fascinating here is the sheer engineering prowess these scientists brought to bear. You've hit on the exact logistical nightmare they faced.
So how did they do it?
Travers actually had to build a custom high-capacity liquid air machine, one that could continuously process massive volumes of atmospheric gas.
Okay, so they weren't just boiling down a cup of air.
No, not at all. They were processing tens of liters of liquid air, which equates to thousands of liters of gaseous air. And they had to do it with obsessive precision, making sure that when the argon finally boiled off, the microscopic droplet of remaining liquid wasn't accidentally lost to the ambient heat of the room.
Man, the stress of that. So they finally get down to this tiny, mysterious residue. And to figure out what it is, they use spectroscopy.
Right.
They vaporize that tiny droplet, trap the gas in a vacuum tube, run a high-voltage electrical current through it, and pass the resulting light through a prism.
Because every element emits a completely unique spectrum of light. It's like a visual barcode.
And the barcode they saw for this remaining gas featured these brilliant green and yellow lines that didn't match anything in the known scientific registry.
They had definitively proven the existence of a new element. And the name they chose, Krypton, from the Greek word kryptos for hidden well, it perfectly encapsulated the Herculean effort required to strip away the rest of the atmosphere just to find it.
Which sets up this really beautiful irony. The element they identified by its brilliant spectral barcode, the one whose name literally means the hidden one, is heavily utilized today specifically because it is blindingly bright.
It's the illuminating paradox. The gas that took a massive industrial machine to coax out of hiding is now engineered to produce absolutely spectacular light in modern technology.
But we need to make a crucial distinction here regarding how that light is actually produced. Because, we just spent several minutes establishing that krypton is a noble gas with a full valence shell.
Yeah, it's famously lazy.
Right. It doesn't react. It doesn't burn.
Yeah.
So if its electron shell is completely full and it fundamentally refuses to interact with anything, how are we forcing it to do all this energetic, violent glowing and flashing? We aren't combusting it. So where's the light coming from?
This raises an important question, and it really highlights the difference between a chemical reaction and electrical excitation.
Okay, break that down for us.
Well, a chemical reaction involves atoms permanently sharing, trading, or stealing electrons to form entirely new substances, right? Like iron reacting with oxygen to form rust.
Or hydrogen burning with oxygen to release heat and light.
Exactly. But krypton will not do that. It always retains its electrons.
Right. So instead of trying to force a chemical bond, we apply a purely physical stressor. When you seal krypton inside a glass tube and run thousands of volts of electricity through it, you are bombarding those stable atoms with a massive jolt of kinetic energy.
And the electrons orbiting the krypton nucleus absorb that electrical energy and physically jump up to a higher unstable orbital state.
But physics demands equilibrium. Those electrons cannot maintain that excited state indefinitely.
No, they can't. Within fractions of a second, they collapse back down to their original stable orbits.
And as they drop back to baseline, the law of conservation of energy dictates that the absorbed electrical energy has to go somewhere.
Yep. It is expelled outward as a photon, which is a tiny packet of electromagnetic radiation.
And for krypton, those photons manifest as a stunning, highly intense whitish blue to violet light. It's a much cooler, more elegant emission than the classic, aggressive red-orange glow you get from exciting neon gas.
It's temporary physical excitation, The krypton atom is zapped, it jumps, it spits out a photon, and then it immediately goes back to being an inert, solitary atom.
And that predictable, repeatable cycle is incredibly valuable. Because krypton produces such a sharp, intense burst of white light, it is the gas of choice for professional, high-speed photography flash lamps.
Yeah, when a camera needs a massive instantaneous wash of pure white illumination to freeze high-speed motion, a krypton-filled flash tube delivers a burst of light that is just far superior to standard LEDs or xenon tubes in certain high-performance contexts.
And it scales far beyond just photography, too. The optics industry harnesses krypton for highly sophisticated lasers. A krypton ion laser utilizes this continuous excitation to produce a powerful, focused beam that can be tuned across several different visible wavelengths.
Particularly in the red and green spectrums, right?
Exactly. And these lasers are utilized in delicate medical procedures, like retinal surgery, where specific wavelengths are needed to coagulate blood vessels in the eye without damaging the surrounding tissue.
We also see its optical reliability deployed in critical infrastructure, specifically high-intensity airport runway lighting.
Oh, that makes sense.
Yeah, imagine you have a commercial airliner descending through thick fog or heavy precipitation. Standard incandescent lighting simply cannot penetrate the gloom.
But krypton can.
Krypton-based approach lights produce this intense, piercing stroboscopic effect that cuts right through adverse weather, providing pilots with absolute visual confirmation of the runway threshold.
So the gas that Ramsey and Travers couldn't even see in 1898 is now actively guiding airplanes safely to the ground. That's incredible.
It really is.
But the utility of element 36 goes far beyond just its optical properties. If we move away from how it handles light and look at how it handles physical mass, we uncover a completely different, hidden superpower. Krypton is exceptionally dense.
Its atomic mass is significantly higher than the nitrogen and oxygen molecules that make up the bulk of our air. Functionally, krypton is nearly 3 times heavier than standard atmospheric air.
Here's where it gets really interesting. You might actually be relying on this rare, heavy element in your house right now.
Oh, definitely. If you live or work in a premium, highly energy-efficient building.
Yeah. Equipped with those high-end double or triple pane windows, the gap between those sheets of glass isn't just a vacuum, and it isn't filled with regular air. Those panes are pumped full of a heavy noble gas, frequently argon, but in ultra-high efficiency windows, they use krypton.
And the reason comes down to thermodynamics and what we call the mean free path of gas molecules.
Which means what exactly?
Now, heat transfer through a window occurs primarily via conduction and convection. The molecules of gas between the panes absorb the thermal energy from the hot side of the window, bounce around, collide with each other, and transfer that kinetic energy to the cold side.
I always picture it like a heavy bouncer at a nightclub. The blazing summer heat, or the freezing winter cold, is trying to penetrate your home. The temperature walks up to the window pane, but stationed between the exterior glass and the interior glass is this incredibly dense, sluggish bouncer krypton.
I love that analogy.
Right. Because krypton atoms are 3 times heavier than oxygen or nitrogen, they require far more energy to move. They don't bounce around easily. So the bouncer just crosses his arms, stubbornly absorbs the impact, and refuses to let the outside temperature cross the velvet rope to the inside pane of glass.
The mass of the atom physically disrupts the kinetic chain. Krypton's thermal conductivity is roughly half that of standard air.
Wow, half.
Yeah. When you inject it into the narrow half-inch gap of a modern window unit, it acts as an invisible, highly dense thermal blanket. It suppresses convective currents from forming between the panes, trapping your expensive heated air inside during the winter and blocking the radiant heat of the sun during the summer.
It is just brilliant engineering. We literally extract an invisible gas from the outdoor environment, seal it inside our walls, and use its sheer atomic sluggishness to protect us from that very same outdoor environment.
We use its mass to insulate our homes, and we use its electrons to power our lasers.
But perhaps the most profound application of krypton's physical properties occurred when physicists used it to literally define physical space.
Oh, you're referring to the redefinition of the meter.
Yes. For decades, standardizing international measurement was a severe headache for the scientific community. The original metric standard was literally a physical object.
Right, the international prototype of the meter. It was a solid bar of platinum-iridium alloy.
Kept in a vault somewhere.
Exactly, in a highly controlled vault in Paris.
But the fundamental flaw with a physical artifact is that it is subject to the universe. No matter how stable the alloy, metal expands when it gets warm and contracts when it gets cold.
It can be scratched, it can degrade, it could theoretically be destroyed.
Right. If your foundational unit of reality is tied to a chunk of metal in France, your entire framework of physics is vulnerable to microscopic fluctuations.
The scientific community realized they needed a standard that was universally constant, something that could be accurately reproduced in a laboratory in Tokyo or New York or anywhere else in the cosmos without relying on a physical artifact.
They needed a constant of nature.
And they found it in the optical properties of the isotope Krypton-86.
Going back to that electrical excitation we discussed earlier,
Yeah.
when you excite Krypton-86, it emits a very specific razor-sharp line of orange-red light. Light travels as an electromagnetic wave, and the physical distance between the crest of one wave and the crest of the next, the wavelength, is governed by the immutable laws of quantum mechanics.
The wavelength of that orange-red emission from Krypton-86 never changes. It doesn't expand on a hot day. It doesn't degrade over centuries.
It provided the perfect, indestructible ruler. Scientists utilized a device called an interferometer, which splits a beam of this krypton light, bounces it off mirrors, and recombines it to create interference patterns.
By precisely counting the microscopic interference fringes produced by those waves, they could measure physical distance with unprecedented submicroscopic accuracy.
So in 1960, the international scientific community officially retired the metal bar in Paris. They formally redefined the meter as exactly 1,650,763.73 wavelengths of the orange-red emission line of Krypton-86 in a vacuum.
That is just mind-blowing precision.
So what does this all mean? For over 20 years, until the definition was updated in 1983 to rely on the speed of light, humanity completely anchored its fundamental measurement of physical space to the atomic behavior of an invisible gas.
Every architectural blueprint, every orbital trajectory calculated for the Apollo missions, every microchip designed during that era, they were all ultimately scaled to the light emitted by the hidden one. If we connect this to the bigger picture, it demonstrates how scientific progression constantly forces us to look past the obvious. We build our societies out of the abundant materials, iron, carbon, silicon.
The stuff we can see and touch.
Right. But when we push the boundaries of extreme precision, whether it's navigating an aircraft through zero visibility or defining the very fabric of spatial dimensions, we have to rely on the rarest, most elusive properties the universe has to offer.
Before we wrap up the journey of element 36, there is an important logistical reality we have to address. We spent this entire time talking about how incredibly heavy and dense this invisible gas is.
Yeah, that it acts as a sluggish thermal blanket and sinks to the lowest point.
Right. So if we are extracting it, purifying it, and pumping it into lasers and window panes, we have to look at the safety profile. If a tank of Krypton leaks in an industrial facility, does this density pose a threat to us?
Well, from a toxicological standpoint, no. Krypton is strictly non-toxic.
Because it's inert.
Exactly. Because it retains that full valence shell and refuses to chemically react, it cannot poison you. If you inhale it, it does not bind to your hemoglobin, it doesn't interrupt your cellular processes, it simply goes into your lungs and comes right back out.
But the threat isn't chemical, it's physical displacement. Because it is nearly 3 times heavier than air, a large volume of pure krypton released into an enclosed room behaves essentially like invisible water.
It will sink immediately to the floor and begin pooling.
Right. And as it pools and fills the room from the bottom up, it forcefully pushes the lighter nitrogen and oxygen upward and outward.
The danger in a pure krypton environment isn't that the gas is actively attacking your biology, it's that it displaces the oxygen you need to survive.
A person standing in a flooded room would asphyxiate simply because the dense krypton has crowded the breathable air out of the space.
It's an asphyxiation hazard purely by way of physical mass. This is why any laboratory or manufacturing facility handling high-concentration noble gases requires specialized, low-level ventilation systems and oxygen monitoring sensors.
But for the general public, encountering krypton inside a shattered double-pane window or a broken camera flash poses absolutely zero risk.
Yeah, absolutely zero. The volumes are so incredibly small, and it disperses instantly into the ambient atmosphere. Under normal conditions, the tiny amount of krypton in Earth's atmosphere is completely safe.
The 1 part per million that surrounds us every day is a testament to its harmlessness in natural concentrations. It's just a silent, heavy spectator to our entire existence.
It really is.
Taking a step back and looking at the full scope of what we've unpacked today, I think Krypton stands as the ultimate proof that an element's greatness and impact on human civilization is not measured by its abundance.
Far from it. Its impact is dictated entirely by our ability to understand its unique atomic architecture.
We are talking about an element so thoroughly hidden in the atmospheric noise that it took liquid air machines and state-of-the-art cryogenics just to prove it existed.
Yet, once we isolated that tiny 1 in a million fraction, we leveraged its electrons to pierce through fog and perform medical surgery.
We harnessed its physical mass to block the harshness of the weather from our homes. We used its unyielding quantum consistency to draw the literal ruler by which we measured the world.
It completely flips the narrative of what makes a material valuable. The most extraordinary tools at our disposal aren't always the loudest, the most reactive, or the easiest to find.
Sometimes the most extraordinary discoveries are the ones hiding in plain sight. The key to the next technological leap might simply be drifting invisibly through the room, waiting for someone to build the right machine to isolate it.
It certainly makes you evaluate the empty space between you and the microphone a bit differently.
It absolutely does. Which brings me to a final thought for you to ponder. If our absolute gold standard for measuring physical reality was once dictated entirely by the light of an invisible gas, a gas humanity inhaled without knowing for hundreds of thousands of years, take another deep breath right now.
Feel the air. Fill your lungs.
What other invisible, completely hidden phenomena are floating in the space around us at this exact second? What incredibly rare forces or unmeasured particles are drifting through your living room, just waiting for the right tool, the right extreme temperature, or the right experiment to reveal them and completely redefine everything we think we know about reality?
That's a profound thought.
Thanks for joining us on this deep dive, and don't forget to subscribe to Atomic 118 because every element has a story and we're uncovering them one atom at a time.